And now we'll look at the next section, which is going to be on metabolism. And for further information, you can look at metabolism and bioenergetics, these separate Wikipedia articles. So it's going further. So all cells require energy to sustain cellular processes, and where energy is the capacity to do work, which in thermodynamics can be calculated using Gibbs free energy. So MES Note, in thermodynamics, work performed by a system is energy transferred by the system to its surroundings. Essentially all has to do with motion, and hence relative motion. One thing relative to another thing, you're going to have work or energy. You have to quantify that as such in that process. Yeah, so this work performed by a system is energy transferred by the system to its surroundings by a mechanism through which the system can spontaneously exert macroscopic forces on its surroundings. In the surroundings through suitable passive linkage, the work can lift a weight, for example. Yeah, for example, a system needs to perform work such as energy transfer, such as from your body to lift a weight. MES subtle note the circular reasoning again. Energy is the capacity to do work, while work is the energy transferred by a system exerting forces on its surroundings. So you're using the definition of you're using the definition of energy, you're using the word energy in the definition for work to define energy. Anyways, continue further. So Gibbs free energy, or Gibbs energy, is a measure of thermodynamic potential energy. Yeah, which is you have energy that has potential to do work. So thermodynamics is a branch of physics that deals with heat, work, and temperature and their relation to energy, radiation, and physical properties of matter. Traditionally, thermodynamics has recognized three fundamental laws, simply named by an ordinal or counting identification. The first law, the second law, and the third law. A more fundamental statement was later labeled as the zeroth law after the first three laws has already been established. And now let's go over some thermodynamics. So the zeroth law of thermodynamics defines thermal equilibrium and forms a basis for the definition of temperature. If two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Two physical systems are in thermal equilibrium if there is no net flow of thermal energy between them when they are connected by a path permeable to heat. And so basically, so if you have two systems, they have the same temperature as a third system, then basically, actually no, it doesn't necessarily be the same temperature, but just in thermal equilibrium with, so if two systems are in thermal equilibrium with a third, then they are with each other, because there is no flow being transitioned. Yeah, flow of heat or energy and so on. So they're going to remain the same. The first law of thermodynamics, so the other one's zeroth law. So this is going to be the first or the second if you include the other one as first. So the first law of thermodynamics states that when energy passes into or out of a system as work, heat, or matter, the system's internal energy changes in accord with the law of conservation of energy. The law of conservation of energy states that the total energy of an isolated system is constant. Energy can be transformed from one form to another, but can be neither created nor destroyed. For a thermodynamic process without transfer of matter, the first law is formulated as this: delta U equals Q minus W, where U denotes the change in the internal energy of a closed system, Q denotes the quantity of energy supplied to the system as heat, and W denotes the amount of thermodynamic work done by the system on its surroundings. Yeah, so basically this is the change in internal energy equals to input, and then this is the output. Input minus the output energy. And so the second law of thermodynamics states that in a natural thermodynamic process, the sum of entropies, which is a measure of disorder of the interacting thermodynamic systems, never decreases. In other words, always getting more chaotic. Another form of the statement is that heat does not spontaneously pass from a colder body to a warmer one. So it goes from a warmer to the colder, not the other way around. Yeah, so, let's continue further. So the third law of thermodynamics states that a system's entropy approaches a constant value as the temperature approaches absolute zero. With the exception of non-crystalline solids, such as glasses, the entropy of a system at absolute zero is typically close to zero. Yeah, so as it gets super cold, then it's approaching zero entropy as well. But the third law says approaches a constant value. And yeah, so some non-crystalline solids could be above 0. Or yeah, it doesn't need to be as close to 0 as these other types of of crystalline solids. And classical thermodynamics considers 3 main types of thermodynamic processes. Yeah, I think this is supposed to be ES right here. And I'm not sure if I copied and pasted from Wiki, or I typed it, so I'll just put it in like this instead of putting the SIC label. So anyways, so we'll have 3 kinds of, classical thermodynamics considers 3 main kinds of thermodynamic processes. 1 is changes in a system, 2 is cycles in a system, and 3 is flow processes. Continue further. So entropy is a scientific concept as well as a measurable physical property that is most commonly associated with a state of disorder, randomness, or uncertainty. Yeah, so going back to that other law, so the sum of entropies of the interacting never decreases. So in other words, it's going to go in more and more chaotic or random. An example would be an ice block. If you have an ice block and it looks like a perfectly ordered block, then if you just leave it outside in the sun, it's going to melt away and spread around randomly in all directions, etc., and not be as ordered as before. So basically it's saying you can have the opposite happen. You're not going to have randomly ice forming up into a perfect cube. I mean, water forming upwards into a perfect cube. Let's continue further. Yeah, actually, one more just an analogy. This one here is a good one here. So you're not going to have heat go from something cold to something warm. So in other words, make this even colder by itself. So it's not spontaneous. Yes, for example, if you go next to a fire, you're not going to get colder. Your heat's not going to move away to that fire. You're going to get warmer. Is the entropy. So is what the law is stating. The first law, the second law of thermodynamics. Going further, so glass is a non-crystalline or amorphous, often transparent solid that has widespread practical, technological, and decorative use in, for example, window panes, tableware, and optics. And pane is just a section of a window or divisions of a window. So, for example, if you have a window like this or like this, and it's separated into 4 panes, you have 4 windows of that one giant window. All right, going further, so absolute 0 is the lowest limit of the thermodynamic temperature scale, a state at which the enthalpy and entropy of a cooled ideal gas reach their minimum value. And it's taken as 0 kelvins. And the fundamental particles of nature have minimum vibrational motion, retaining only quantum mechanical or 0-point energy-induced particle motion. The theoretical temperature is determined by extrapolating the ideal gas law by international agreement. Absolute 0 is taken as minus 273.15 degrees on the Celsius scale, which is a part of the International System of Units, which equals minus 459.67 degrees on the Fahrenheit scale, which is the U.S. Or the United States customary units or imperial units. And here is just a temperature scale illustration, a thermometer here. So 0 kelvins is at right here. 0 kelvins is at negative 273.15 degrees Celsius and is defined as absolute 0. And then if you go to 0 degrees, that's 273.15 Kelvin. And then at 0.01 degrees, that's 273.16. And if you go to 100 degrees at boiling water temperature, that's 373.15 Kelvin. Yes, and then enthalpy. So this is where enthalpy and entropy is at a minimum. State of which of these of an ideal gas is at a minimum. And where enthalpy is a property of a thermodynamic system and is defined as a sum of the system's internal energy and the product of its pressure and volume. So again, energy is a lot to do with motion. So pressure is how much things are being compressed, and hence you'll have a higher vibrational motion when you look deep into that atoms. And so it's related to the volume and pressure. And the ideal gas law, so basically enthalpy is just the internal sum of the internal energy. And the ideal gas law, also called the general gas equation, is the equation of state of a hypothetical ideal gas. It is a good approximation of the behavior of many gases under many conditions, although it has several limitations. So the ideal gas law is often written in an empirical form, PV equals nRT, where P, V, and R are the pressure, volume, and temperature, and N is the amount of substance and R is the ideal gas constant, and which relates average kinetic energy of gas particles with temperature. Again, energy, temperature, heat, etc. is just ways of describing motion. So 0-point energy, or ZPE, is the lowest possible energy that a quantum mechanical system may have. Unlike in classical mechanics, quantum systems constantly fluctuate in their lowest energy states. In other words, you have a vibrating ether or aether at all times, which is very fascinating stuff. And then the 0-point law is where the Kelvin is derived from. Let's just go back to the Kelvin right here. Where absolute zero is absolute zero uses the ideal gas law. So extrapolates or takes from the ideal gas law, so it expands it all the way down, and then you're going to have that absolute zero temperature defined as this. So very, very fascinating stuff indeed. All right, so let's continue further here. So according to the first law of thermodynamics, energy is conserved, i.e. cannot be created or destroyed. Hence, chemical reactions in a cell do not create new energy, but are involved instead in the transformation and transfer of energy. Nevertheless, all energy transfers lead to some loss of usable energy, which increases entropy or state of disorder, as stated by the second law of thermodynamics. So as a result, living organisms such as cells require continuous input of energy to maintain a low state of entropy, or a high state of order. So because it's every time there's energy transfer, you're going to be increasing entropy or increasing disorder. So you need constant energy input to add order to the cells and the whole body. In cells, energy can be transferred as electrons during redox or reduction-oxidation reactions, stored in covalent bonds and generated by the movement of ions, e.g., for example, hydrogen, sodium, potassium, across a membrane. And now let's look at more in depth on redox. So redox or reduction-oxidation is a type of chemical reaction in which the oxidation states of atoms are changed. The oxidation state, sometimes referred to as a oxidation number, describes the degree of oxidation or loss of electrons of an atom in a chemical compound. And conceptually, the oxidation state, which may be positive, negative, or zero, is a hypothetical charge that an atom would have if all bonds to atoms of different elements were 100% ionic, with no covalent component. This is never exactly true for real bonds, and this figure is from, this one's compoundchem.com, and it shows you the oxidation states here. It's a bit, you have to zoom in to them. Let's see, I'll just do a big zoom in right here. Let's see how close I can get here. It should be pretty high revolutions here. Actually, let's just go use this, or go straight to this one. I'm just going to zoom back out, just because it's easier to zoom in on the actual website. So you click that website, and you go here, click to enlarge. So this is the thumbnail, but if you click to enlarge here, it shows you in a very big size here, and you zoom in, and now you can see these much better. So for example, here, if you look at carbon, the oxidation states could be -4 or +4, depending on how many electrons it has in its orbitals, or and so on. And there's some other oxidation states you could have here. So this cobalt can be -3 or a -1, 0, etc. And so there's a whole lot of information in this image right here. We'll make this bigger. And hydrogen could be -1, 0, or +1. So this is the known oxidation state is +1, and then the common one is the circle ones here, and then this other one, oxidation state not known, if it's grayed out or not in there. So there's a grayed out there. So very fascinating stuff. And let's just go back here. So oxidation describes the degree of oxidation or loss of electron of an atom in a chemical compound. And you can think of it as basically a hypothetical charge an atom would have if all the bonds were of different elements were 100% ionic instead of sharing the electrons. It's actually just ionic, just using the electrostatic force there. So going further, so oxidation is the loss of electrons or an increase in the oxidation state of an atom, an ion, or of certain molecules. So when these are when the shells are occupied with electrons, oxidation goes down. But then when you lose those electrons, so now you have, you lose electrons, now you have an increase in oxidation state, and you could also view it as, well, if you add an electron, or if you add the electron, you're adding a negative. So adding electron goes down, removing it goes up. And reduction is the gain of electrons, because you're reducing by, you reduce oxidation state because you're gaining electrons which are negative charge. So reduction is the gain of electrons or a decrease in the oxidation state of an atom, an ion, or of certain atoms in a molecule, and a reduction in, which is a reduction in oxidation state. Hence the word reduction. So reduction is you're decreasing the oxidation state. In other words, you're reducing an oxidation state. And now here's an illustration comparing reducing agents and oxidizing agents. This figure 11, this one's from chem.librarytext.org. So reducing agent reduces other substances. I bold this one just to make it very clear. And loses electrons. So here's a reducing agent right here. So it's a reducing agent. What it would do is it would lose electrons, thus gain an oxidation state for this one, but it would make this one reduce. So you give the negative charges to this B, and this B is reduced. And therefore its oxidation state increases. An oxidizing agent oxidizes other substances. So there's an oxidizing agent. Here what it will do is gain electrons. So we'll take the electrons from A, so then this would be reduced. So this agent itself will be reduced, but it's oxidizing others by taking the electrons, taking the negative charge away, so then it has a plus oxidation state. So basically you're taking negative charges away. You can look at it like that. And its oxidation state decreases here, even though it oxidizes others. So gaining electrons equals decreasing oxidation state. Losing electrons equals increasing oxidation state. A reducing agent increases oxidation state by losing electrons. I just want to illustrate that very deep in your brain here. So a reducing agent, what it would do is it would increase its oxidation state by reducing others, by losing electrons, and then it gives it up to this one here, and this one gets reduced because you're gaining electrons. So while it's increasing its oxidation state. An oxidation agent or oxidizing agent, oxidizing agent decreases oxidation state by gaining electrons. So going back here, so oxidation state, this gains electrons, and when you gain electrons, you reduce the oxidation state, but it's taken from this one. So this one's oxidation state is going to go up. So A is oxidized. It's going further. So many reactions in organic chemistry are redox reactions due to changes in oxidation states, but without distinct electron transfer. For example, during the combustion of wood with molecular oxygen, so just the burning of wood, of O2, the oxidation state of carbon atoms in the wood increases, and that of the oxygen atoms decreases as carbon dioxide and water are formed. So it's not always just dealing directly with electrons. You're dealing with electrons on atoms already. And water are formed. The oxygen atoms undergo reduction, formally gaining electrons, while the carbon atoms undergo oxidation, losing electrons. Thus oxygen is the oxidizing agent, hence the name, and carbon is a reducing agent in this reaction. So basically the most common burning or redox reaction is just burning of wood, and so wood burns with molecular oxygen, which is O2, and so the oxygen, it gains electrons, so then it's when it gains electrons, it reduces its oxidation state, but it oxidizes others, increases the oxidation state of the carbon or in the wood, because the wood loses electrons. So thus oxygen is the oxidizing agent, and carbon is a reducing agent in this reaction. Combustion or burning is a high temperature exothermic redox chemical reaction. Exothermic gives off energy between a fuel called the reductant and an oxidant, usually atmospheric oxygen. And this oxidant is that's just another term for oxidizing agent. So oxidizing agent. like that. So an oxidant oxidizing agent, usually atmospheric oxygen, which is O2, that produces oxidized, often gaseous products. Oxidized, they are reduced in electrons, or they lost electrons. Often gaseous products in a mixture termed as smoke. Combustion does not always result in fire because a flame is only visible when substances undergoing combustion vaporize, but when it does, a flame is a characteristic indicator of the reaction. And smoke is a collection of airborne particulates and gases emitted when a material undergoes combustion or pyrolysis. Yeah, so pyrolysis, which is thermal decomposition without oxygen, but it's combustion when it's with oxygen, together with the quantity of air that is entrained or otherwise mixed into the mass. Yeah, so all stuck inside there. This is the air inside that mixture. Particulates, also known as atmospheric aerosol particles, or atmospheric particulate matter, or particulate matter PM, or suspended particulate matter SPM, are microscopic particles of solid or liquid matter suspended in the air. The term aerosol commonly refers to the particulate / air mixture as opposed to the particulate matter alone. So here's a bunch of different types here and their sizes. So this diagram shows types and size distribution in micrometers, or which is about 0.001 millimeter, or again a millionth of a meter. And this is of atmospheric particulate matter. So you have gas molecules right here. This is these are in millimeters here. In micrometers. So here's this very, very small here. Gases, contaminants, and then just to see the differences, here's viruses are said to be this small over there. And here's another one. Suspended atmospheric dust. You have smog, tobacco smoke, soot, and so then you have bacteria being 1 micron in size. They're 1,000 times bigger than a nanometer, and this one could be considered as 10 nanometers. This one is actually no, not 10 nanometers. This is 1,000th of a nanometer. This would be 100th of a nanometer. This would be 10th of a nanometer. This would be nanometer right here. The gases contaminants are about a nanometer in size. They're very fascinating. So then this is just the scale. These are logarithmic scales. You times it by 10 each one. And you have pollen all the way to 10 micrometers, and so on. Oil, smoke, flash ash, cement dust, settling dust, heavy dust is over to 100 times bigger than gaseous contaminants or soot, and tobacco smoke, and so on. And just cat allergens are at this size, which is pretty small, and house dust mite allergens, and so on. Let's continue further. Yeah, actually, I just forgot to read this column over here. Let's just go over this one quickly. So this is the gas molecules here, and this is particulate contaminants, and this is the range of the sizes and the types. And this is types of dust right here: suspended atmospheric dust, settling dust, heavy dust is bigger. And then these are the biological contaminants from the different variations in sizes. And interesting that viruses are so much smaller than all these other biological contaminants. It's very interesting. So let's continue further. So here's the an exothermic reaction. So figure this one here. I got this from this is from chemistrylearner.com. So this is exothermic, where energy is released. That's what the exothermic, and endothermic is energy is obtained. Yeah. So this is an exothermic reaction. So here's burning of wood or combustion. So the heat goes away. So here's the typical chemical reactions. You have wood represented as C, and then X and HY, which these could be different numbers. And then you'll have Y, usually this is the formula, so Y divided by 2 plus 2X. Oxygen, and this is times by, then this is of O2. Yeah, so this is a formula to get a number to represent the typical types of reactions here. Then O2, then you have the CO2, and then X, carbon dioxide, which forms carbon dioxide. And then you have Y divided by 2 of H2O, water. Water vapor plus heat, and this is the heat is the exothermic part, where it's releasing heat or energy to the environment. Yeah, so here's the wood CH, and then you have the O2 reacting with it. You get the fire, and so on. And again, the flame itself is as if the components vaporize, but it's almost always happens in typical reactions. But if they don't vaporize, you'll have it. You could have it with no flame, but you'll still have a combustion and a lot of energy release. So you just won't be able to see this. But it could still be explosive and very hot. And now let's look at this from the redox side. So here's an example. This figure is of, this is from forestchemistry.com, no, forestchemistry.weebly.com. So combustion of methane gas, and the methane gas CH4. And yeah, so here's the redox reaction. So you have CH4 plus 2O2, so that's the oxygen. And what ends up happening here is this one has 8, or this has an oxidation state of -4. Yeah, that's the carbon that has a -4 oxidation state. So that means, yeah, let's first actually go back to that oxidation state and read up on that again. Just go back to just get a refresher quickly. So oxidation state is right here. It's sometimes referred to as an oxidation number. Describes the degree of oxidation or loss of electrons of an atom in a chemical compound. And conceptually, the oxidation state, which may be positive, negative, or zero, is the hypothetical charge that an atom would have if all bonds to atoms of different elements were 100% ionic with no covalent component. And this is never exactly true for real bonds. So if we go back to here, so this one's -4. So this is a charge we would have if all the bonds, all the bonds to other elements. In this case, H, hydrogen, is ionic instead of covalent. So if this was if this was ionic, this would be a -4, because right now it would have 4 bonds, or 4 of the electrons are stuck with hydrogen, or shared with it, so that it's a those are covalent bonds. But if they were ionic, this would be a -4 charge. And so in this reaction, what happens is, so this one right here, this C, this carbon, it is oxidized from -4 to +4. In other words, it's going to lose 8 electrons in this reaction. This is going to go 8 electrons going to lose. Then it's an oxidation state of +4. And then if we look at this O2, this oxidation state is 0. And then this, it's 0, but then it goes to -2. And so see what happens to the electron. So this C loses 8 electrons. So it goes from that -4 to +8 oxidation state. And then this O2 is the one that's picking up the electron. So it is the oxidizer. So it's the oxidizing agent, but it itself gets reduced because it's picking up electrons. And see what happens to it. So then this 2 of these O2s, the oxidation states become -2 of each one of these. So that means that's 4 electrons here. Because that's 2, yeah, so then that'd be -2 and another -2, so that'd be -4 total. And then, yeah, so I'll just leave it like that, so to indicate electron. And then this here is 2H2O, so there's 2 O's. And each of these O's is going to be an oxidation state of -2, so they pick up, each oxygen picks up 2 electrons. That's going to be another 4, so that's going to be 8 electrons. Like that. So this is the reaction that occurs there. So one carbon atom is oxidized from -4 to +4. And then 4 O atoms are reduced from 0 to -2. And then you have 4 H atoms remain unchanged at +1. So these ones, the oxidation state of all the hydrogens are just +1 in all of them. This is +1, nothing changes with that. And yeah, so that is the this is the redox reaction. So oxygen is the oxidizer of the carbon, or the oxidant, or the oxidizing agent. So it's very, very fascinating. So let's just read up on these other notes right here. So carbon oxidation state increases. In other words, loses more electrons. And then that's carbon. Yeah. Then oxygen oxidation state decreases and it gains more electrons. Oxygen increases C's oxidation state. So oxygen increases C, carbons. And then C decreases oxygen's state. So C could be considered a reducing agent. So C reduces the 0 into negative, or that the oxygen with a 0 state to a negative. And then C is a reducer, carbon is a reducer, and oxygen, or O, is an oxidizer. So yeah, it's very fascinating. So although oxidation reactions are commonly associated with the formation of oxides, which contains at least one oxygen atom and one other element, and in this case right here, it's oxygen atom with one other element, in this case C, right there. So you have an oxide there, so this is carbon dioxide. Yeah, so although oxidation reactions are commonly associated with the formation of oxides from oxygen molecules, oxygen is not necessarily included in such reactions, as it's not necessarily, does not need to be included, as other chemical species can serve the same functions. And going further, so redox reactions can occur relatively slowly, as in the formation of rust, which is iron Fe oxide, iron, which is Fe oxide, or much more rapidly, as in the case of burning fuel. So rust and burning fuel is the same. They're both redox reactions. One's slow, one's fast. And so rust is an iron oxide, usually reddish brown oxide formed by the reaction of iron and oxygen in the catalytic presence of water or air moisture. So water acts as the speeding up of the reaction. The iron oxides are chemical compounds composed of iron and oxygen. And oxygen is the quintessential or perfect example of oxidizer. So it's a quintessential oxidizer, hence the name oxygen, hence the name oxidizer, for referencing oxygen. Right, going further now, so metabolism is the set of life-sustaining chemical reactions in organisms. The three main purposes of metabolism are the conversion of food to energy to run cellular processes, the conversion of food/fuel to building blocks for proteins, lipids, nucleic acids, and some carbohydrates, and the elimination of metabolic wastes, which are toxic remains that can't be further used by the organism. These enzyme-catalyzed reactions allow organisms to grow and reproduce, maintain their structures, and respond to their environments. Metabolic reactions may be categorized as catabolic, which is the breaking down of components. For example, the breaking down of glucose to pyruvate, or I think it's pronounced pyruvate, by cellular respiration. Or anabolic, which is the building up or synthesis of compounds such as proteins, carbohydrates, lipids, and nucleic acids. Usually, catabolism, catabolism releases energy, and anabolism consumes energy. So yes. So MES Note, pyruvic acid. Yeah, just to illustrate this point right here. So breaking down of glucose to pyruvate. MES Note, pyruvic acid, which is CH3COCOOH, is the simplest of the alpha keto acids with a carboxylic acid and a ketone functional group. And pyruvate, so this is just a type of acid. So pyruvate, which is the conjugate base, CH3COCOO minus, is an intermediate in several metabolic pathways throughout the cell. So a metabolic pathway is a linked series of chemical reactions occurring within a cell. Yeah, and this conjugate base, so this means that if this is an acid, and then if it loses one of the H, it becomes a negative, and then that acid, its conjugate base when it removes that is the pyruvate. Yeah, so basically this is it's conjugate a related base based on this one. So it loses the H, becomes this pyruvate. Going further, so right here, yes, if we go here, I just want to make this maybe a bit smaller, just to include this in there, a bit bigger here. And going back here, so metabolic pathway is a series of reactions, and then pyruvate is usually an intermediate in several of these metabolic pathways throughout the cell. And this is just a type of acid with carboxylic and a ketone functional group. And here, just quickly pause video and just added ketone. So so forgot to add this definition. A ketone is a functional group with a structure R2C. Then this equals 0 or double bond equal oxygen, where R can be a variety of carbon-containing substitutions. Yeah, so basically a structure like that. And going further, so here's a illustration. We could even make this bigger now. So here's an example of an enzyme catalyzed exothermic reaction. So you have this is the energy, and this is reaction coordinate, or just indicating that when the reactants are becoming products, the process of it. So if you have reactants such as C6H12O6 plus O2, so this is a redox reaction right here. So this is the amount of energy, required to get the reactants to the product. So what you'll have is these you're going to need a lot of energy here. So without an enzyme to speed up the reaction, you're going to need a lot of energy all the way up to here. This is activation energy without enzyme. And this activation energy could be thought of as basically like temperature. So with an enzyme, you're going to need a higher temperature to get this to react. So yeah, even if you have, let's say, a redox reaction, if it's super cold, freezing, you might not even get it. But with an enzyme, you could speed that up and get it lower than what you typically would need. So yeah, and here I just quickly added this note here, MES Note. So activation energy is the minimum amount of energy that must be provided for compounds to result in a chemical reaction. For a chemical reaction to proceed at a reasonable rate, the temperature of the system should be high enough such that there exists an appreciable number of molecules with translational energy equal to or greater than the activation energy. So again, this has a lot to do with motion. So energy equals motion, or relative motion, or both relative and absolute motion. But is it something to think about? So anyway, so this is a energy you need. Activation energy without enzyme goes all the way high here. Then you get to the products, and the overall energy released during the reaction is over here. So this is the reactants, the amount of energy in this side, and then the products will have less than the reactants, and you're going to give off this amount of energy released. And the other energy is put into the actual breaking of the bonds and the rebonding with other elements and so on. But then if you had with an enzyme to speed up the reaction, you might just get it even less than half the amount of energy required, or temperature and so on. And activation energy with enzymes all the way up, just up here, and then goes all the way back to the products. Fascinating stuff. Let's continue further. So the chemical reactions of metabolism are organized into metabolic pathways in which one chemical is transformed through a series of steps into another chemical, and each step being facilitated by a specific enzyme. Enzymes are crucial to metabolism because they allow organisms to drive desirable reactions that require energy that will not occur by themselves, and by coupling them to spontaneous reactions that release energy. Yeah, so the enzymes have that additional step of you coupled with, or additional benefit of coupled with other reactions, the spontaneous reactions that release energy. So if you have some of them that just release energy, notice how reactants to products release energy. So you couple that with enzymes that speed up this process to release energy. You're going to have a mechanism for producing a lot of free energy to be used for other reactions. So enzymes act as catalysts. They allow a reaction to proceed more rapidly without being consumed by it. And so they don't need to be consumed by it, by reducing the amount of activation energy needed to convert reactants into products. Enzymes also allow the regulation of the rate of a metabolic reaction, for example, in response to changes in the cell's environment or to signals from other cells. So with the presence of the enzymes, or if you remove them or limit how much is inside, you could regulate or speed up or slow down the rates of reactions of specific processes. And going further here, and now I just want to make another note. This is going to be on fermentation, and the reason is because the next section is cellular respiration, and further information can be found at cellular respiration and fermentation wiki articles. So just to illustrate just for fermentation before we dive into cellular respiration. So fermentation is a metabolic process that produces chemical changes in organic substrates through the action of enzymes. And substrate right here is typically the chemical species being observed in a chemical reaction, which reacts with the reagent to generate a product. So the substrate is the one you're looking at. And then you add a reagent to generate a product. So going over here. So it's so fermentation is a metabolic process that produces chemical changes in organic substrates through the action of enzymes. In biochemistry, it is narrowly defined as the extraction of energy from carbohydrates in the absence of oxygen. So a general definition is produces chemical changes in organic substrates through the action of enzymes. So you have a substrate with an enzyme there, and then you get, so you have chemical changes. But specifically in biochemistry, you're narrowed down strictly to extraction of energy from carbs or carbohydrates without oxygen. So in the absence of oxygen. In food production, it may broadly, in food production, it's usually defined like this, or considered or referred to as. So it may be more broadly referred to any process in which the activity of microorganisms bring about a desirable change to a foodstuff or beverage. And the science of fermentation is known as Yeah, zymology, and this is from Greek, the workings of fermentation. So fascinating. Going further, so some countries list a legal definition of food, often referring them with the word foodstuff. So this is the so any change to a foodstuff or beverage, and that is basically legal definition of food in some countries. So fascinating stuff.